Imagine a world where the past can be altered, where what we observe changes reality itself. This isn't science fiction. It's the astonishing world of quantum mechanics. Quantum mechanics explores the strange behavior of matter and energy at the smallest scales. It challenges our everyday intuition, revealing a universe stranger than we could have imagined. In the quantum realm, particles exist in a blurry haze of possibilities, their fates intertwined. Light possesses a dual nature, behaving as a wave in some situations and as particles in others. This wave-particle duality is one of the many mysteries that quantum mechanics seeks to unravel. One such experiment, the quantum eraser experiment, stands as a testament to the bizarre and counterintuitive reality of the quantum world. In the early 20th century, physicists began to probe the atom's structure, discovering a realm where the classical laws of physics break down. This realm, governed by the laws of quantum mechanics, is a place where particles can be in multiple states at once, where information seems to travel faster than light, and where the act of observation fundamentally alters the system being observed. The quantum eraser experiment is a profound demonstration of this last point, highlighting the crucial role of the observer in quantum mechanics. To grasp the mind-bending implications of the quantum eraser experiment, we must first journey back to one of the foundational experiments in quantum mechanics, the double-slit experiment. The double-slit experiment, a cornerstone of quantum physics, first unveiled the wave-particle duality of light. It provided early hints of the strange, interconnected nature of the quantum world. It is in the echoes of this experiment that the quantum eraser finds its roots. Understanding its intricacies is crucial to appreciating the profound implications of the quantum eraser experiment. The quantum eraser experiment takes the strangeness of the double-slit experiment a step further, introducing the concept of delayed choice. Imagine setting up the double-slit experiment and then, after the light has already passed through the slits, choosing to observe or not observe which path the light took. Astonishingly, the quantum eraser experiment suggests that this delayed choice can influence the outcome of the experiment. Some physicists interpret the results as evidence for backward causation, the idea that the future can influence the past. Others propose alternative explanations, but the debate highlights the fundamental mystery surrounding the nature of time and causality in the quantum world. The quantum eraser experiment, however, is not just a theoretical curiosity. Its findings could have profound implications for the development of new technologies, particularly in the field of quantum computing. Before we can dive into the quantum eraser experiment, we must first understand the experiment that serves as its foundation, the double-slit experiment. At the heart of the double-slit experiment is a simple question: how does light behave when it encounters an obstacle? Imagine shining a beam of light at a solid barrier with a single, narrow slit cut into it. On the other side of the barrier, you place a screen to observe the light that passes through. As you might expect, the light passing through the slit forms a bright band on the screen directly behind the opening. Now, imagine adding a second slit to the barrier, creating two narrow openings close together. Instead of two distinct bands, a pattern of alternating bright and dark bands, known as an interference pattern, appears on the screen. This pattern is a hallmark of wave behavior and is not what we would expect if light were solely composed of particles. The interference pattern observed in the double-slit experiment provides compelling evidence for the wave nature of light. However, the story takes an unexpected turn when we consider the quantum nature of light, specifically its particle-like behavior. When we reduce the intensity of the light source in the double-slit experiment to the point where only one photon is emitted at a time, something truly remarkable happens. Even when photons are sent through the slits one by one, the interference pattern gradually emerges on the screen. Each photon, in a sense, seems to be interfering with itself. According to quantum theory, particles like photons do not follow well-defined paths. Instead, they exist in a superposition of states, a blurry haze of possibilities, simultaneously passing through both slits. This wave-particle duality is one of the most profound mysteries of quantum mechanics, challenging our intuitive understanding of the nature of reality. The strangeness of the double-slit experiment doesn't end there. Let's introduce another layer of complexity to the experiment. Imagine that we place detectors at each of the slits to determine which slit each photon passes through. Surprisingly, when we introduce these which-path detectors, the interference pattern on the screen disappears. The act of observing which slit the photon passes through seems to destroy its wave-like behavior, forcing it to choose a definite path. Instead of the characteristic alternating bright and dark bands, we observe two distinct bands on the screen, as if the photons were now behaving as classical particles. The act of observation, of gaining information about a quantum system, inevitably disturbs that system. The double-slit experiment lays the groundwork for understanding the even more mind-boggling quantum eraser experiment. The quantum eraser experiment takes the intrigue of the double-slit experiment to a whole new level. It introduces a seemingly impossible twist: the possibility of erasing the which-path information after the photon has already passed through the slits, and in doing so, recovering the lost interference pattern. The quantum eraser experiment builds upon the double-slit experiment with the addition of a clever mechanism: entangled photons. Entanglement is a bizarre phenomenon where two particles become linked in such a way that they share the same fate, no matter how far apart they are. In the quantum eraser experiment, a pair of entangled photons is generated. One photon from each pair is sent through the double-slit apparatus, while its entangled partner is diverted to a separate detector. By manipulating the entangled partner, we can indirectly obtain or erase information about the path taken by the photon passing through the slits, even after it has already done so. This delayed choice aspect of the experiment raises profound questions about the nature of time and causality in the quantum world. The quantum eraser experiment, while conceptually mind-boggling, relies on a surprisingly simple setup, albeit one that requires exquisite precision and control over the quantum world. At its core, the experiment involves the same basic elements as the double-slit experiment: a light source, a barrier with two slits, and a screen to observe the pattern of light. However, the quantum eraser introduces a few key additions that allow us to manipulate and erase the which-path information of the photons passing through the slits. Our journey begins with a laser, a source of coherent light, meaning all the light waves are in sync. This laser beam is directed towards a special crystal known as a beta barium borate, BBO crystal. This crystal can split a single photon into two entangled photons, each carrying half the energy of the original photon. The entangled photons, now traveling along separate paths, encounter the heart of the experiment, the double-slit apparatus. By manipulating the idler photon, we can indirectly influence the fate of the signal photon, even though they are spatially separated. Entanglement, often described as spooky action at a distance, lies at the heart of the quantum eraser experiment. This bizarre quantum phenomenon allows two particles, in our case photons, to become linked in such a way that they share the same fate, regardless of the distance separating them. Measuring the state of one entangled photon instantly determines the state of the other, as if they were communicating faster than the speed of light. To understand how entanglement enables the quantum eraser, imagine our entangled photon pair born from the same quantum event within the BBO crystal. These photons are like two coins flipped at the same time, intrinsically linked. If one coin lands on heads, we instantly know the other coin must land on tails, no matter how far apart they are. In the quantum eraser experiment, the polarization of the entangled photons is the key. This correlation in polarization states is the spooky action that allows us to manipulate the fate of the signal photon by manipulating its entangled twin. With our entangled photon pairs, we explore quantum erasing. We erase the which-path information of the signal photon by manipulating the idler photon's polarization. Polarizers filter light by polarization. We influence the signal photon. Entangled photons share correlated states. Measurement destroys entanglement. Polarizer orientation preserves or erases information. Erasing information restores interference. It's like altering past events. Observing the unobservable. Detecting the interference pattern. The quantum eraser experiment culminates in the observation of the interference pattern, or lack thereof, on the screen behind the double slits. However, directly observing the interference pattern with the naked eye is impossible. The photons, after all, are quantum entities, their behavior governed by probabilities and wave functions, not the deterministic laws of classical physics. To detect the subtle dance of light and shadow that constitutes the interference pattern, physicists employ sophisticated detectors strategically positioned on the screen. These detectors, highly sensitive to the arrival of individual photons, act as the eyes of the experiment, recording the arrival time and location of each photon striking the screen. As photons accumulate on the detectors, a pattern begins to emerge. If the witch path information has been preserved, two distinct bands of light will form on the screen, corresponding to the two slits. This pattern resembles what we would expect if light were composed of classical particles, each photon traveling through one slit or the other. However, if the witch path information has been erased, a remarkable transformation occurs. Instead of two distinct bands, an interference pattern, characterized by alternating bright and dark bands, gradually emerges on the screen. This pattern, a hallmark of wave-like behavior, indicates that the photons have somehow interfered with themselves, even though they were sent through the slits one at a time. Variations on a theme exploring different erasing techniques. The quantum eraser experiment, like a captivating melody, reveals new nuances of the quantum world. Physicists use ingenious techniques to erase witch path information, each with unique insights. One method uses light polarization to encode witch path information. Rotating the idler photon's polarization can preserve or erase this information. Other techniques exploit photon momentum, direction, or wavefront shape. Delayed choice experiments add intrigue, suggesting choices can be made after detection. These variations highlight the richness and subtlety of the quantum world. The resurrection of interference, a quantum paradox. The quantum eraser experiment shows the interference pattern can be recovered by erasing witch path information. This paradox challenges our classical notions of cause and effect. In the quantum world, information shapes reality. Erasing information reveals a deeper layer of reality. The quantum eraser experiment underscores the profound role of the observer in quantum mechanics. Observation is an active intervention that disturbs the system. The quantum eraser experiment shows that the observer effect is not limited to conscious observation. Any interaction revealing information about a quantum system can collapse its wave function. This suggests that measurement plays a crucial role in shaping reality. The quantum eraser experiment highlights the crucial role of information in the quantum world. Information, in the context of quantum mechanics, is not merely a collection of data. It is a fundamental property of physical systems, intricately linked to the very fabric of reality. The experiment demonstrates that manipulating quantum information can have profound and seemingly paradoxical effects on the behavior of quantum systems. In the classical world, we are accustomed to thinking of information as something that can be copied, deleted, or manipulated without affecting the physical world. In the quantum realm, however, information is tightly bound to the systems it describes. The act of gaining information about a quantum system inevitably disturbs that system, potentially altering its state. The quantum eraser experiment demonstrates that even erasing information can have a profound impact on quantum systems. Erasing the witch path information does not simply delete data. It changes the very nature of the system, restoring its wave-like behavior and revealing the interference pattern that was seemingly lost. This intimate connection between information and reality has profound implications for our understanding of the universe. It suggests that information is not just a useful tool for describing the world, it is a fundamental ingredient in its construction. The universe, from this perspective, is not just a vast collection of matter and energy, but also a complex web of information, constantly being exchanged and reshaped through quantum interactions. The quantum eraser experiment challenges our understanding of time. In the classical world, time flows from past to future. The past is fixed, the future unwritten. But in the quantum realm, this may not hold. Erasing which path information questions if the past can change. It suggests the past may exist in a superposition of states. The implications for our understanding of time are profound. Time may be far stranger than we ever imagined. Beyond common sense rethinking reality, the quantum eraser experiment, with its counterintuitive results and mind-boggling implications, forces us to confront the limitations of our classical intuition when exploring the quantum world. The rules that govern the universe at its most fundamental level are not the rules we experience in our everyday lives. Concepts like wave-particle duality, entanglement, and the observer effect challenge our very notions of what it means for something to be real. The quantum eraser experiment highlights the importance of embracing uncertainty and accepting the limits of our classical understanding when venturing into the quantum realm. It is a reminder that the universe is far stranger, more mysterious, and more awe-inspiring than we could have ever imagined. It is a call to let go of our preconceived notions and approach the unknown with a sense of wonder and open-mindedness. The quantum eraser experiment is not just a mind-bending thought experiment. It is a testament to the power of human ingenuity and our insatiable curiosity to unravel the mysteries of the universe. It is a reminder that the more we learn about the universe, the more we realize how much more there is to learn. The journey into the quantum realm is a journey into the unknown, a journey that promises to challenge our assumptions, expand our horizons, and ultimately lead us to a deeper understanding of ourselves and the universe we inhabit. A universe redefined, shifting paradigms. The quantum eraser experiment redefines our understanding of reality, challenging classical notions of locality and the role of the observer. It reveals a universe interconnected in ways that defy our everyday intuitions. Observation is not passive, it actively shapes reality. Embrace a new paradigm where information and observation are fundamental. The quantum technology frontier, from speculation to reality. Quantum mechanics is reshaping technology, promising a revolution. Quantum computers, using qubits, perform calculations exponentially faster than classical ones. Entanglement is crucial for quantum computing, enabling powerful computational networks. Quantum cryptography offers unbreakable encryption, revolutionizing data security. Navigating the ethical labyrinth, quantum choices and consequences. As we stand on the precipice of the quantum era, we must confront the ethical implications of wielding such powerful and potentially disruptive technologies. The quantum eraser experiment reminds us that quantum technology is a mirror reflecting our choices and their consequences. Quantum computers hold immense promise but also raise concerns about potential misuse. They could crack encryption, compromise security, and disrupt society. We must establish ethical guidelines to ensure responsible use of quantum technologies. Our choices will paint the landscape of the quantum era. The never-ending quest. Embracing the enigma. The quantum eraser experiment, for all its mind-bending implications, is not a destination but a starting point. It is a single spark illuminating the vast and mysterious landscape of quantum mechanics, a realm where our classical intuitions often fail, and where the very nature of reality seems to shimmer and shift before our eyes. It is a call to embrace the unknown, to question our assumptions, and to embark on a never-ending quest to unravel the deepest mysteries of the universe. The experiment serves as a potent reminder that the more we learn about the universe, the more we realize how much more there is to discover. Each answer we uncover only leads to more profound questions, pushing the boundaries of our knowledge and challenging us to expand our horizons of understanding. The quantum eraser experiment, with its paradoxes and enigmas, should not be seen as a source of despair or confusion. Instead, it is an invitation to embrace the beauty and wonder of the universe in all its strangeness and complexity. It is a reminder that the journey of scientific discovery is not about finding all the answers, but about learning to ask the right questions, to challenge our assumptions, and to remain open to the possibility that the universe is far more extraordinary than we could have ever imagined. Shadows and light, a quantum shadow play. Imagine a darkened room illuminated by a candle behind a screen with slits. The light casts intricate patterns of light and shadow on the wall. These shadows represent the wave-like nature of light. Introducing a detector, the interference pattern vanishes. The shadows become distinct blobs of light. This captures the essence of the quantum eraser experiment. Observing the path destroys the interference pattern. Manipulating light can restore the interference pattern. The quantum eraser is like a cosmic shadow puppet show. Embrace the interplay of light and shadow to understand the quantum world. The cosmic coin toss. Flipping reality with every glance. Imagine a cosmic coin spinning in space, existing in a superposition of possibilities. Observing it forces it to collapse into a definite outcome. The quantum eraser experiment can reverse this, returning it to superposition. Our observations shape reality, flipping the cosmic coin with every glance. The quantum eraser, a beacon in the tapestry of discovery. The quantum eraser experiment illuminates the uncharted territories of quantum mechanics. It is a journey into a realm where classical physics melts away, replaced by particles and probabilities. This experiment compels us to confront the limitations of our everyday intuition. It challenges our assumptions about reality and the role of the observer. The quantum eraser hints at a universe far stranger and more interconnected than we imagined. It extends into philosophy, technology, and ethics, shaping our future.